Okay, good morning, everyone. Let's get started. Today we're going to use Pad to discuss our course content because I want to write on something, or to show something, and then later for the artificial neural networks, especially how we're gonna explain the back propagation. I'm gonna using this marker or pen to write down the detailed steps of back propagation. Okay, so first of all, we're gonna release homework 4 today, which is all about SVM. So of course, we're gonna wrap up SVM today. So you should have enough content to start with homework 4. But again, I'll suggest you to looking at homework 4 immediately after the class, especially for the programming section. As we discussed before, it doesn't have like any like very much working load for the programming. However, to solve the SVM dual, which is the constraint convex optimization problem, we request you to investigate some existing libraries. Okay? You do need to look at, for example, if you're using Python, we suggest that you use like SciPy optimize, and there's one particular type method is called SLQP or something like that, right? So you do need to look at documentation. You do need to try that, right? You need to you do need to self-learn how you're gonna call those libraries to implement your SVM dual optimization problem, right? And so it's better to get started early. And if you have some problem, you can come to the office hour and ask, like, interact with our TA or you and me about how to call that library, right? But if you start doing that like 1 hour before a deadline, it might not be helpful. Right? Okay, so in the last lecture, we another thing, we also released the deadline for the final project report. I think it should be December 19th. That means 4 days after the final exam. So it should have sufficient time, and we are unlikely to extend that because we have some due on posting the final grade. So we would like to post this deadline early so that you got sufficient time to make a plan. Okay? So don't try to request for extension for the final project report because the administration office, register office won't allow us to submit grades like after their deadline, right? Unless you have to go through a very complicated procedure. Okay, so in the last lecture, we talked about SVM dual, right? How?
I have a question. Can we build upon the midterm report or should final report be examined?
What do you mean by building upon? Yeah, feel free to do that. Right. So as if you can take a look at the course web page, right? So we asked you to write down a few parts, your midterm report, in the final report, right? We're not gonna say, okay, because your ranking is not better than others, or your experimental results are not good. That won't be the place which trigger a points deduction. But if we do find some places like we want you to write down there, but there is not, then that kind of points, that part of points will be deducted. Okay. So that's the policy for the grading. Okay. Okay, going back to what I just said, right? We have in the last lecture we have discussed the SVM dual, right? SVM dual, we have some through a series of like simplification, we can reduce the SVM dual optimization problem into a convex optimization problem, right? So let me briefly write down, right? So it becomes a minimization problem again, right? It's a half, and this is goes through. Suppose you have n training examples, right? So there's a double summation, right? And in the SVM dual problem, we only optimize a set of Lagrange multipliers, right? Alpha I, alpha j. If you can remember, they correspond to Lagrange multipliers for the function margin constraints, right? And here's yi, yj, which are labels of examples I and example j, and xi transpose xj, right? And subtracted by the summation over the Lagrange multipliers, right? So it's a typical quadratic objective function, but you have to consider constraints, right? Two type constraints. First is that each alpha I is between 0 and c. The second one is that the summation of alpha I, yi is are simply equals to 0, right? Those are all derived from the dual form, right? Dual form is max min, and then you first solve the inner minimization problem, and you substitute results into the Lagrange function, you get maximize problem. Of course, you take negative over the remaining objective, you convert it to a minimization problem, right? So it's a lengthy procedure. It's not hard, but it does contain a bunch of steps you need to take care of. So, and also by connecting the dual solution of primal solution, we got a conclusion that once you optimize the dual problem, suppose your optimal variables are alpha I star, right? Then we can recover the optimal weight vector by weighted summation of the training inputs, right? So each training input xi is weighted by alpha I star multiplying with yi, right? This is a known structure. And also we point out that actually many in practice, many of alpha I stars are simply 0. So actually the optimal V vector is only determined by those training inputs with non-zero alpha I stars, right? Those training inputs are called support vectors, right? So, and also, we can also use KKT conditions to recover the optimal bias parameter B, right? Which I'm not gonna repeat. But if we look at the prediction step, right, we know that from the primal form, right? Suppose we got optimal W star and B star, given test input X, our prediction is to compute the dot product between W star and X plus B star, right, which is the classification score, right? We take the sign, right? So from the dual solution, it tells us that the optimal weight vector is a weighted summation over the training inputs, right? So we can substitute this for W star into our prediction, right? So that means the dot product between W star and test input is simply a weighted summation again, right? Over every training example, for every training example xi, you need to compute dot product between xi and x, right? Then weight this product by alpha I star and yi, right? This is simply replace W star by this guy, and you immediately get these results, right? So what does this result tell, right? So imagine, like recall that we talk about how do we extend our linear classifiers to nonlinear classifier, right? One easiest trick will be, okay, if in the original input space, I cannot find a hyperplane to separate out positive and negative examples, right? And then I want to make some kind of smart feature mapping or feature transformation, right? So suppose this is a original feature vector, which is might be in the D space, right? D-dimensional vector, right? Now, after some feature mapping, right? Some smart feature mapping, I mapped X into a higher dimensional space, which is might be like big D, right? So usually big D is much larger than small d. So in this higher dimensional feature space, we denote by phi x the mapped feature vector, right? We believe those vectors will be more easily linearly separated, right? Then if we can find out such a fit, right? Such a feature mapping, right? Then the remaining task will be, okay, in the map to feature space, we find out a weight vector and bias parameter, right? So that means if you want to do this trick, right, you can first perform the feature mapping phase, right? And map all the training inputs in the higher dimensional space. And then in that space, you run SVMDUE, right? You run SVMDUE to solve alpha I stars and then use the structure again and substitute it back to the prediction. Then you got the prediction score here, right? So if you want to compute the prediction score for a new test input X, right? So first, we're gonna do some feature mapping. You get a higher dimensional feature vector. You do the dot product with the W star, and because W star is now represented by a weighted summation over the mapped training inputs, right? So you just substitute back, and you got this dot product B is like summation over all the training examples, or for each training example, you calculate the feature mapping of Xi, and calculate feature mapping of the test input X to do dot product, the weight is dot product by alpha I star, and the ground truth label Yi, right? Everyone is comfortable, right? So now let us take a closer look at this result, right? So because right now our goal is to extend our linear classifier to perform some nonlinear classification. We assume that, okay, we'll have some powerful feature mapping phi. After this feature mapping, in the new feature space, we can find they are linearly separable. Right? So for convenience, let us represent this dot product after feature mapping as a function of two inputs, right? And X and Z, right? So we can view like this function takes two inputs X and Z as inputs, and then compute the dot product of feature mapping of X and feature mapping of Z. Right? And then we can simply, replace in the prediction score, right? The prediction score, we can simply replace this phi X transpose phi Z by this K function, right? So then your prediction score now is to compute this by input function over every training example, right? The by inputs includes Xi and X for every training example I, right? Then you multiply or weighted by alpha I and Yi and then plus the bias parameter D, right? Someone asked, what's meaning for this, right? You just define a function as this, right? And then you just substitute this dot product after phi feature transformation by this function, right? There seems no meaning at all, except that you just change the notation, right? Of course, if in the computation of K itself, if you follow the exact definition, that is, we first compute the feature mapping of X, and then feature mapping of Z, and do a dot product, then such kind of notation change is not meaningful at all, right? You just replace this guy by another symbol, right? But what if I tell you that we can compute this guy much more efficiently? In other words, we won't compute this guy following the exact definition. First, to do some feature mapping and do a dot product. Instead, we just compute in the original feature space. Then the benefit will show up, right? Because I got another way to compute this function, right? In this new way of computing, we no longer need to perform explicit feature mapping and then do the dot product in the high dimensional feature space. Then it will gain a lot of computational efficiency. So let me give you a concrete example, right? For example, if your X and Z are some vector of say 300, 3000, dimensional, right? No, sorry, 1000 dimensional, right? But your feature mapping, really, it is higher dimensional than the original feature space. I can just write a random number. Its dimension can be 1 million, right? So if you compute this guy, exactly following the definition, that means you first compute a feature mapping for X and Z. That means you have to generate or calculate 2 1 million dimensional vectors, right? And then you do element-wise product over these 2 vectors and sum together. That's the definition of dot product, right? So that means you have to compute at least in the level of 1 million complexity, right? But if we can find a way to avoid explicit feature mapping on dot product, right? If we can find a way to compute this guy such that my operation is only inside the original feature space, so the term complexity will be just aligned with the dimension of the original feature space, which is just the 1000. Then the cost is dramatically reduced. So that's the motivation, or that's the idea. So let me summarize again, right? If we have to compute phi, that is the feature mapping, every time anyway to fulfill this function, then we gain nothing. However, if I compute the value of k without explicitly writing the blown up representation, right, the feature mapping, then we'll have a computational advantage. Right? So that's where the so-called kernel trick kicks in. Okay, so next we're going to use a very concrete example to show the value of the kernel trick. Right? So this example is called polynomial kernel. So suppose we're given 2 examples, X and Z, right? And our feature mapping is simply to enumerate the polynomials and cross product of those elements in these 2 features, right? So here we restrict the order to be 2. That means we want to map the features in X and Z to some at most quadratic terms, quadratic order terms, right? So for example, here is a n-dimensional feature vector X, right? So so you can see that this is a mapped feature vector, right? It consists of all degree 0 terms, which is simply 1, right? And then all degree 1 term is just the copy of the original feature values, x1 to xn, right? And then the remaining is all degree 2 terms, right? So you can view like I'm just enumerate pairs of feature elements, right? Of course, it can duplicate itself, like x1 squared, x1, x2, x1, x3, x1, x4 onto x1, xn, right? The x2 squared, x2, x3, x2 is 4, x3, xn, into x2, xn, right? So it's relatively straightforward to compute the dimension of the feature mapping, right? So for all degree 0 terms, it's just 1 term, right? Just 1 features, right? How many degree 1 terms do we have? Just n, right? And how many degree 2 terms do we have? What? I mean, how many degree 2 terms do we have? What? 2n? Any other thought? Yeah, like you just need to count, like, so like x1 starting from x1 itself, and then x2 to xn, right? And x2 starting from x2 itself, x3 to xn, right? You don't need to do the x1 again because that's already there. So you just count this is n, this is n minus 1 until 1, right? So this will give you let me erase all of them. N plus n over 2, right? So overall, we know that the dimension of the mapped feature vector will be at level of n squared, right? N is the dimension of the original feature vector. So back to the discussion we have done a minute ago, right? So we know that, okay, our feature mapping actually maps, sorry. An input vector from n dimensional to a n squared dimension. Right? If we take n to be 1000, right? And we know that after feature mapping, the dimension of the mapped feature vector will be at level of 10 to the power of 6, 1 million. Right? So now, if we want to compute the dot product between two mapped feature vector, the time complexity will be at level 1 million. Right? So of course, it's not cheap at all. Right? So imagine just compute two. For a pair of example x and z, right? Just compute the dot product after feature mapping. Just for one pair, it will take you around 1 million operations. Right? That's really, really expensive. So we compute dot product A, which is phi x transpose phi z, will take the time like 1 square, right? Which is quite expensive, right? Even for n is a moderate, right? Just 1000. How do we reduce the computation cost? Right? So here we introduce another way to compute this dot product. Right? We compute it in this way. We denote this computation result as B. Right? So we first do the dot product between x and z. Remember here, we never do some quadratic feature mapping. Right? We just compute the dot product between x and z in our original feature space, then plus 1, then take square. Okay. So what's the cost of computing B? Just ON, right? I mean, if this guy is n-dimensional, right? Because the dot product of two n-dimensional vectors just ON, right? Because just do the like n animal-wise product summation, right? It's ON, and plus a scalar and take square, right? So this will just take the complexity of ON. Right? Does it make sense? Okay. But here, we want to claim that actually the result of A and the result B are equivalent. The only difference is in the coefficients. I would like to say like the coefficients actually do not matter. Why do not matter? Because you can just adjust the weight a little bit to make the prediction scores exactly the same. Right? So the key is that, okay, you need to ensure the terms are the same. So now let us check why the results of A and B are equivalent. So I'm gonna use just like a two-dimensional vector to showcase that, right? But it can be generalized to n-dimensional, right? So here's x, right? X is defined as x1, x2, right? So similarly, I can do the feature mapping over z, right? Which is z1, z2. Now just write down the feature mapping. 1, z1, z2, z1 square, z2 square, z1, z2. Right? I just follow feature mapping. I just replace x by z. Does it make sense? Okay. So now I just follow the definition, right? You follow the definition to compute A, which is to do the dot product between these two mapped feature vectors, right? Well, which is really tedious. You just do the item-wise product of every element of these two vectors, right? And add them together, right? Let's just do it together, right? This is really tedious. So 1 versus 1, and x1 z1, and then x2 z2, and then here and here, right? So you got x1 square, z1 square, x2 square, z2 square, and then the cross term, right? x1, x2, z1, z2, right? You just multiply this two vector. You just do the dot product of these two vectors, right? Let's just follow the definition. You first do some explicit feature mapping, and then you do the dot product. Okay. So now let us check the result B, right? So remember the computation B never does any feature mapping, right? We first do the dot product between x and z and +1 take square. Right? Let's see what happened here. Right? So here, so first x transpose z, what's that? x1 z1 plus x2 z2, right? So x1 z1 plus x2 z2, then you take square. Okay. And next we just expand is the square of the summation, right? I don't know if in your high school there's some like formula you need to recite to do this expansion, but in my home country we do recite that. So now I never feel headache about doing this expansion of summations, right? You just remember you're gonna write out the square terms individually, and then you just enumerate the cross terms, right? Multiply by 2. That's it. Right? So we got 3 terms in the summation, right? We first write down their square, which is 1 plus x1 square, z1 square, x2 square, z2 square, right? Then we just look at the cross terms, right? There are 3 terms, the cross term will be 3 terms. And remember, we just multiply 2. Right? So just 2x1 z1, 2x2 z2, and then 2x1 x2 z1 z2, right? Then the next task is to contrast these 2 results. Right? So 1 here in A and 1 here in B. Right? So x1 z1 here, 2x1 z1 here. Right? x2 z2 here, 2x2 z2 here. Right? And the remaining are square terms, right? So x1 square, z1 square, x1 square, z1 square, x2 square, z2 square, x2 square, z2 square, and finally x1, x2, z1, z2, and 2x1, x2, z1, z2, right? So actually all the terms in A and all the terms in B, they have like 1-to-1 match. Right? The only difference is the coefficients. Right? As we just mentioned, the coefficient doesn't matter. Why it doesn't matter? Because like if you use phi to construct some feature mapping, right? You got some weight vector, CW star, right? This is your prediction score, right? And if you write down the computation as B, right? It actually corresponds to another slightly different phi x, right? The difference is only in the coefficient. So you can just adjust the corresponding element in W to get the same result. Right? That's why the coefficient never is a concern. In other words, if we really want to make this exactly the same, right? What we need to do is that, okay, for this guy, I'm gonna multiply with square root, right? Square root 2, right? And for this guy, I'm gonna multiply a square root. And for this guy, I'm gonna multiply square root. Right? Then you do this, you compute A with explicit feature mapping, you exactly get B. Right? Does it make sense? Right. So what do this result conclude? It actually opens the way to save the computation, right? If we can find out a smarter way to compute the result of map dot product of the mapped feature vectors, right? You can save a lot of computation. Okay? So for any method to fulfill this kind of idea, this is called kernel trick. Okay. And this function is called kernel function. Okay, so here we give some like a more formal definition of kernel trick, right? Suppose we want to compute some kernel function of by inputs x and z, right? Which is essentially first performing some feature mapping phi over x and z respectively, and then do a dot product. Right? The kernel trick means that we can save the time and or space by computing this value of kernel function by performing operations in the original space without the explicit feature transformation. So this is called kernel trick. Okay, any questions so far? Yeah. Yeah, exactly. You will change it to be D, and D is the whatever order you want. This is called polynomial kernel. Other question? Okay, great. Hopefully this example will give you an intuition why kernel trick is useful and what kind of magic it plays. So as a comparison, right? We use this example of doing degree 2 polynomial features, right? Vx. If you do the explicit feature mapping, right, and then do the dot product, then you have to operate over the vectors of quadratic length, right? So this is just the length of the mapped feature vector we just calculated together, right? And then if you apply the kernel trick we just mentioned, right? K, x, and z equals to 1 plus x transpose z t squared. Then the kernel trick allows you to save time and space and compute the dot product in the original n-dimensional feature space, right? And things will become even clear that you consider general case like degree D, right? If this degree D, you can imagine the dimension of the map, the feature vector will even higher, right? Even more crazy. Right? And we still have the general kernel function is called 1 plus x transpose z to the power of d. So the complexity of computing the kernel function is still linear complexity in the original feature vector's dimension, right? And but on the contrary, if you want to do the explicit feature mapping, imagine that you want to enumerate all possible degree 1 terms, degree 2, degree 3, degree 4 onto degree D. That will be a lot. Okay, so next we're gonna have we're gonna introduce the properties of kernels. Right? We're gonna summarize this kernel trick and definition of kernel functions in a more general way. So we have seen that, okay, looks like if you can compute some by input function efficiently, we can save a lot of like time and space without explicitly performing feature mapping, right? The question would be, can we use any by input functions? Or can we define any function of 2 inputs and just return some value? And we'll see, okay, it is some kind of like a kernel function corresponding to explicit feature mapping, corresponding to some high dimensional feature mapping to a dot product. The answer is no, right? Yeah, if the answer is yes, it's so easy, right? It's so easy for the kernel trick. Actually, for arbitrary by input function, right? of course, we assume that these two inputs I can see are of same dimension. Right? This function is a valid kernel function only if it corresponds to an inner product in some feature space. Right? So that means if you want to claim that some given function, right, you can come out arbitrary function, right? You want to claim that this is a feature, this is a kernel function, then you must show that okay, it corresponds to some unknown feature mapping phi, such that after you performing feature mapping over X and the feature mapping over Z, then do a dot product, this value is the same as the function value. Then this case called a valid kernel function. Right? And here I want to emphasize that this phi can even be infinite dimensional. So actually, in the later when we discuss about RBF kernel, which is very common use kernel, the feature mapping actually is infinite dimensional. In other words, for infinite dimensional feature mapping, you will never be able to explicit compute it, right? Because you are not able to you really cannot explicitly compute an infinite dimensional vector, right? And given two infinite dimensional vectors, you are not able to really compute their dot product, right? Because the cost is infinite. So in that case, you have to seek for the kernel trick. Right? You need to avoid explicit feature mapping, right? But still manage to compute the value. Right? Okay. So then, how do we show that for an arbitrary function? I'm not going to use a key, like for arbitrary function CH, right? Which is a function of two inputs of the same dimension, right? How do we show that this guy is a valid kernel function? Right? And one way is that, okay, I'm just composite some kind of feature mapping and show that, okay, the value of H is the same as dot product after the feature mapping, right? This is one way of doing that. But this is really tricky for real case, right? So in general, how do we show that for arbitrary function K or H, it is a valid kernel? We're going to construct the so-called Gram matrix. And we can show that for any set of finite set of input vectors, the Gram matrix computed based upon your candidate kernel function. If this matrix is always positive semi-definite, then we claim that this function is a valid kernel function. Okay, so what's the definition of Gram matrix, right? So first, let us review the definition of a positive semi-definite, right? We call a symmetric matrix M is positive semi-definite if for any non-zero vector Z, we have this quadratic form non-negative. Right? So Z transpose MZ is a scalar, is a number. If this number for arbitrary non-zero vector Z is a non-negative, then we say M is positive semi-definite. Right? This is the basic definition in linear algebra. I think everyone has heard this before, right? Okay. So positive semi-definite, this is very, very important property of matrices, right? It's not only useful for this piece of definition, but also useful in numerous other places. So if you feel like strange or feel uncomfortable with this definition, I will definitely suggest you to get familiar with that. Right? It is really, really important. Also, if a matrix is positive semi-definite, it has a lot of other properties, like all the eigenvalues are non-negative. Right? Okay, so now let us come to the definition of Gram matrix. Suppose we're given a set of n vectors. This n is finite n, right? So it could be 100, could be 1,000, could be 1 million. It doesn't matter, but it must be finite. Right? So we're given a set of finite vectors x1, xn, right? So we can use these n vectors to construct an n by n matrix G. And each element Gij is computed by the dot product between ith vector and jth vector, namely xi transpose xj. Okay. So if you write out this grand matrix, right, it is just x1 transpose x1, x1 transpose x2, blah, 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 x1 transpose xn. Right? This is the first row. And x2 transpose x1, x2 transpose x2, da da da, x2 transpose xn. We just emerge every row until the last row, xn transpose x1, xn transpose x2, and xn transpose xn. So this is called grand matrix. If we write all the vectors, or if we stack them all together, right, as a matrix, so x1 transpose, each row is a vector, right, until xn transpose, right? So this is a n by d matrix. Then we can write down G simplest as x transpose. You can test it by yourself. Right? Our conclusion is that grand matrix is always positive semi-definite. Does it make sense? Or anyone can show this following definition. Okay, we can review this linear algebra stuff together, right? So according to the definition of positive semi-definite, that means okay for any non-zero vector z, right? So we need to ensure that z transpose gz is non-negative, right? So we're gonna leverage this structure, right? So remember, this x is just a stack, just stacking all the n vectors, right? Row wise, right? So we just replace g by the representation in terms of x, right? We just look at, okay, what if this z transpose x, x transpose z? What about this value, right? So this guy is a vector, right? And what about this guy? This guy is the x transpose z, then take transpose, right? Right? Then you just move this down, right? So x transpose z. Right? So you can see this is a vector, this is a vector, right? This is a vector v. If we denote v as x transpose z, they're essentially v transpose v, right? So this essentially, this number essentially is the dot product of a vector and itself, right? And this must be a non-negative. Right? So now I'm showing that the grand matrix is always a positive semi-definite. Right? Does it make sense? Right. I mean, if you feel like uncomfortable for this, it's fine. Right? I mean, after class, you can follow this derivation. It's just like very standard practice of maybe homework 1 or homework 2 of your linear algebra class. Right? Nothing strange. Okay. So now, based upon this result, like imagine if you have a function t and x and z, right? If there's really a valid kernel function, that means it must correspond to some feature mapping phi over x and feature mapping phi over z, then do the dot product, right? So the idea is that, okay, if I apply phi over this x1 to xn and use that to construct a Gram matrix, that Gram matrix should be a positive semi-definite as well. Okay. Then, how do we check if arbitrary K is a valid kernel, right? I just pretend this is true, right? And then I apply this K over every pair of x1, x2, x2, x3, or xi, xg to construct a Gram matrix, and then check if this Gram matrix is positive semi-definite. So that's the idea. So we're going to construct a kernel matrix, right? So this kernel matrix, every element Jij is a kernel function over xi and xg. So you can imagine, well, here maybe we use big K will be easier, right? So this guy is K x1 until K x1 xn, right? And K x2 x1 until K x2 xn, right? And K xn x1 until K xn, right? You also got a matrix, right? N by N matrix. If this guy, this K, is really some feature mapping, and then do a dot product, right? Then this kernel matrix must correspond to some Gram matrix, right? It's something like that, right? It's like, okay, I applied phi over every x1 to xn, then I construct the Gram matrix, right? So if K is valid, then the kernel matrix must be some Gram matrix. And then because Gram matrix is positive semi-definite, and then this K matrix must be a positive semi-definite. Does it make sense? Right? Does it reasonable? Is it reasonable? Any questions so far? Different phi will correspond to different G. Like once you fix phi, right? You can apply it to all the n vectors here. You actually got n another vector, right? And then you use n another vectors to construct G, right? But it doesn't matter because this G will always be a positive semi-definite, right? And then the point is that this allows us to verify if for arbitrary two input function K, if it is valid kernel, right? If it is valid kernel, and then there must be some phi associated with K, right? And then the kernel matrix must correspond to some Gram matrix, right? Because it must be each K xi xj must be phi xi transpose with phi xj, right? So that means, okay, if this K, I mean, this K is really a valid kernel, then each K xi xj here will be some dot product of the mapped feature vectors, right? Then the whole K matrix corresponds to some Gram matrix of the feature mapping. And the Gram matrix doesn't matter, right? It doesn't matter if you have some feature mapping or not. It always positive semi-definite, and that means the K matrix must be a positive semi-definite always. Any questions so far? Yeah, I want to give you some intuition why this called the Mercer kernel theorem tells us that, right? But of course, if you want to rigorously show that, there are some additional steps, right? But here we just give you the result, right? This is called the Mercer's condition. Right? Let K and xa to any function that maps two n-dimensional vectors to some real number. Right? K is a valid kernel if for every finite set of vectors, and for every any choice of real value C1, C2, and so on, this double summation is non-negative. This essentially is to compute a kernel matrix K over these vectors, right? This set of vectors. Then look at this quadratic term, right? And this guy is non-negative, just means this kernel matrix K is positive semi-definite. Right? This is called a Mercer's condition. So basically, if you want to show that your self-made function is a valid kernel, right? You can just show that, okay, for every finite set of inputs, you use that to compute a kernel matrix. That kernel matrix is always positive semi-definite. Then you can claim that, okay, your own version of this K function is a valid kernel. Any questions so far? Yes, yes. Like I can come out any, like for example, I can give you a function here of z, say x times z. Oh, sorry, it's not x times z. This is it must be a number, right? So maybe x element wise multiplying with z and dot product with 1, right? Or maybe just the sum over xi zi, right? I can come out whatever function I want, right? It's just give you like two inputs and then you give a number, right? But this does not necessarily be a valid kernel, right? How do we show that this is a valid kernel? We need to test with this, right? No, this condition is just used to test if any function of your interest is a valid kernel. Yeah. But later we'll discuss that actually you don't want to use this very often. In most cases, it's just okay based upon the existing kernel. How do we smartly combine them to give a valid kernel? Okay, so here we give a few commonly used kernels, right? Polynomial kernels. Right? So the simplest kernel is called linear kernel. Right? You just do the dot product between x, z. Actually, you do not do any feature mapping, or your feature mapping is just identity mapping, right? And polynomial of degree d is you take the dot product between x and z and take the power of d. And polynomial kernel up to degree d is that you add your dot product between x and z plus c and take the power of d. And you can show that actually this guy corresponds to you enumerate polynomial of degree 0, polynomial of degree 2, 3 until d. This much higher dimensional factor, and then do the dot product. So all interactions of order d or lower. So here, this one is called Gaussian kernel. Gaussian kernel is perhaps the most common used kernel. So it is computed as follows. It's like a Gaussian distribution density. Right? So you first compute the difference between x and z and take the square null, and divide it by some positive constant c, and take minus and take exponential. Right? So c here is called a free parameter, right? And x minus z square norm is called square Euclidean distance, right? So as one of the most commonly used kernel, right, the corresponding feature mapping is infinite dimensional. Okay? So I will leave two exercises for you. First, we show that this kernel is a valid kernel. Second one, show that the mapped feature space is infinite dimensional. Yeah, try to think about that. It might appear in the homework 4. It might appear as a bonus question. I forgot, but it's always good to think about that. It's a very well-known example. Okay, how do we construct new kernel? Right? Of course, you can composite a kernel function, a composited function like arbitrarily, right? And then use Mercer's condition to test that. But it's usually it's not very convenient to show that because you have to show a very general case, like for arbitrary finite set of inputs, you construct kernel matrix, which is positive semi-definite. Right? So here we have a bunch of rules that you can construct new kernels from existing ones. Right? So first, this is a valid kernel K. Right? If you simply multiply a positive constant C, then this kernel is still a valid kernel. And if you multiply this kernel by an arbitrary function x multiplied to x and x prime, like your new kernel is like this, right? Let me denote it by x and x prime. Right? You first apply f of x, and then apply x prime, and then you multiply k x prime with fx and f of x prime. Then this new function is still a valid kernel. Or you can use your kernel function value as input to some polynomial function, then this polynomial function is still a valid kernel. Or you take exponential of a kernel function, then it's still a valid kernel. Okay. So now this gives you a hint to show how the Gaussian kernel here is valid kernel. Okay. If you got two kernel functions, like K1 and K2, you simply add them together, it gives you another valid kernel. If you multiply them together, it gives you another valid kernel. If you want to construct some explicit feature mapping, of course, on your construction, that feature mapping might not be very, very high dimensional. Right? So, and then after feature mapping, you throw them into a third valid kernel, then the result kernel will still be valid. Okay? So this actually has a known instance. It's called deep kernel. Okay? So what's a deep kernel? Right? You threw your input x and x prime into some neural network. Phi here is a neural network. Right? Of course, neural network output can be some multi-dimensional vectors. Right? And then you put this neural network into neural network outputs into some knowing kernel, like RBF kernel. This kernel is called a deep kernel. Right? Of course, this deep kernel is simply just an instance of this composite kernel. Right? If you got some symmetric positive semi-definite matrix A, then the X transpose A X prime is also a valid kernel. Okay. Any questions so far about kernel tricks and kernel functions, and how do we construct new kernels? Okay, so now we just need 1 or 2 slides to discuss how we're gonna embed kernel trick into SVM, which we call nonlinear SVM. So remember, through the previous discussion, right? We can convert the primal SVM to the dual SVM and through some kind of simplification, right? This is our dual optimization problem, right? In the dual optimization, we know that we're gonna do the double summation over every pair of training example, xi and xj, right? And alpha i's are the variables we want to optimize, right? So you can see that actually in our objective function, we need to compute every pair, the dot product between every pair of xi and xj, right? So consider that if we have some feature mapping, nonlinear feature mapping, and we want to learn our SVM in a mapped feature space, then xi transpose xj will be replaced by the dot product of the mapped feature vectors, right? That's basically say, okay, I just apply phi over every training inputs, so I got new feature space, and then I learn my SVM there, right? And then this dot product, according to the kernel trick, we can explicitly compute some kernel function instead, right? Rather than doing this feature mapping and dot product. It gives this here, right? So that means in our SVM dual form, we can simply replace the dot product between every pair of training inputs by the kernel function of the every pair of inputs, right? Then it is equivalent to performing some kind of nonlinear feature mapping in a higher dimensional space and then solve SVM in that space, right? But you never need to explicitly write down the feature mapping or perform the feature mapping over those training inputs, right? Then you just solve that. And it doesn't change the optimization problem at all because this guy is just some constant, just some knowing constant. You're optimizing alpha I and alpha G, right? You just change the coefficients. So all the other computation is the same. Right? You just apply some quadratic optimization package. Does it make sense? Right? So just replace the dot product by the kernel function. That's it. Then, once you solve this optimization problem, of course, you got your optimal Lagrange multipliers, alpha I stars, right? And we know that the optimal weight vector, W star, is the weighted summation over the mapped training inputs, right? And of course, we don't know what this explicit feature mapping is, right? Because we're using kernel function, right? However, what we need is to make the computation, right? We need to make prediction, right? We just need to compute the score here, right? And the score requires us to compute the dot product between the W star and Phi-x, right? So that means if you substitute the structure into this dot product, you're actually doing the summation over the training inputs, and where for each training input, you compute the dot product of the mapped feature vector for xi and mapped feature vector for x, right? So you can see that now it still is the dot product between the mapped feature vectors, which can be further replaced by the kernel function. Does it make sense? Right? So now you just replace this guy by the k function again. So that's it. You never need to explicitly compute W star. You never need to explicitly compute phi. That is a kernel SVM or nonlinear SVM. And similarly, to recover the bias parameter B, you use the exact same procedure, because when you find out the right alpha G star, right between 0 and C, the B star is just the Y corresponding label subtracted by this score, right? And this score again is computed by the kernel function. Okay, so before we move to here, like any questions so far? So you can see that you transit from linear SVM to nonlinear SVM is very, very trivial, right? From practical perspective, right? You just replace the objective function, those pairwise in the product by pairwise kernel function. And in the prediction step, of course, you just compute the kernel function between every training input and the test input and do the weighted summation. That's it. Okay. But how to arrive at this step? It needs a pretty length chain of reasoning. Okay. So that's why in your implementation, you'll find it's really easy to implement kernel SVM. Okay. It doesn't need 10 lines of, it just need 10 lines of code, right? However, you need to know how we can use this, right? How can we get to this step? Okay, any question? Great. So just to showcase, right? If you use Gaussian kernel, right? So remember, in the Gaussian kernel, you essentially first map the original training inputs to some infinite dimensional feature space, right? Remember, Gaussian kernel, as we just mentioned, it corresponds to some infinite feature mapping. So you can imagine in some infinite feature mapping, you're trying to find out a hyperplane which separates positive and negative examples, right? Of course, you cannot visualize the position and support vectors in infinite dimensional space. So here we just give a sense like, okay, if you find out the hyperplane in a infinite dimensional space, we can map back in the original feature space where is the margin, where is the hyperplane look like, right? Of course, in the original feature space, it won't be a linear hyperplane. It'll be some curve, right? So this will be the classification hyperplane. This those bolded line, and then those points, those circled one, are the corresponding support vectors. Just to give you a sense. So now we have finished the introduction of SVM. Is a bit lengthy topic, right? We introduced the dual form of SVM, which can lead to the concept of support vectors. And to make a final prediction, we're going to use the solution structure of the dual form so that we can compute dot products. This actually gives us the chance to apply the kernel trick. We just replace dot product by the kernel function. You're essentially or implicitly doing some feature mapping and then do a dot product, right? So the kernel trick is a computational trick to compute dot products in a higher dimensional space. And want to make a note that the kernel trick is not only applicable to SVMs, right? So actually you can extend perceptron as well. You can use kernel trick to implement your kernel perceptron, right? This is a bonus question in our homework 4. If you're interested to gain that extra bonus and trying to do that, it'll be fun. Okay, any questions so far? Okay, in the remaining 10 minutes, I will quickly introduce the cross-validation. Right? I assume that many of you have heard of this before. So, but here we want to give a more systematic introduction of cross-validation. Right? So, what is cross-validation? So again, is a general strategy or most effective, or most widely used strategy to select the model hyperparameters in your application. So in general or in practice, how do we build a model, right? So we need to collect the trained data. We need to set the hyperparameters, and also we need to define the loss function. Right? And under these hyperparameters, you kind of like optimize the loss function, you get model parameters. Right? Then the question is, how do we know the best hyperparameters? Right? So for example, in perceptron, right, how many epochs should we go through from data, right? And in SVM, how do you choose C? Right? If you can remember, the objective of SVM is a regularizer which encourage the large margin, right? And also the hinge loss. Right? I'm now writing down hinge loss, right? So C is kind of like trade-off between the regularizer and hinge loss, data loss. Right? So I got a question. Right? All right, let me write down the hinge loss explicitly, right? So it will be max 0, 1 minus function margin. Right? So I want to ask, right? Can we joint optimize C here during the training? Right? We know that we optimize W, right, and the B, right, during the training, right? So because we don't know how to set C, right? So my question is, can we joint optimize C as well? Can we? Any guess? Let's try to optimize that. Right? So if we want to optimize, that means we want to minimize the whole objective function, right? In terms of W, B, and also C, right? So if I want to make this whole objective as small as possible, what will be optimal value for C? What? Yeah, as small as possible. Right? And here we require that C must be non-negative, right? Remember, this guy is hinge loss is non-negative, right? So if you want this whole objective to be as small as possible, I can simply set C equal to 0, right? Because this guy is always a positive, non-negative, at least, right? So if you want this whole objective function to be as small as possible, I can simply set C to be 0. And what's the consequence if C is 0? If C is 0, then the hinge loss, which represent how well you fit data, vanish, right? It doesn't take any effect. Of course, it's not what you want. I don't want to only maximize margin without controlling the training error, right? That will make my generation error bound to be very large. Right? This is just one case to showing that all hyperparameters, they usually cannot be joint optimized with model parameters, right? Not to mention another set of hyperparameters like max number of iterations, right? Learning rate, you can even not, you even do not know how to optimize it, right? Can you compute the gradient with respect to the maximum iterations? It's very hard. Then the question is, how do we identify the best hyperparameters? Right? So a commonly used strategy is called k-fold cross-validation. Right? So the idea is that, okay, I want to compare if I applying a particular setting of hyperparameters, what is the generalization performance? Right? Right? Since the training data is there, right? I assume I cannot acquire new data, right? So to test the generation performance, what I can do is just, okay, I'm going to separate this data. I'm going to partition the data, right? I use part of the training data to train with this particular setting of hyperparameters, and then I test the result on the remaining data set and see how it performs, right? Because the training and test are separated, right? They're not overlapping. At least they can indicate some generation performance, right? That's the idea of the cross-validation, right? So let us look at the detailed steps, right? So we're going to split data into k equally sized parts, and the k usually choose as 5 or 10, right? So we use 5 as an example, right? We partition the data into 5 parts, right? And then each time I'm going to use one part for testing and use the remaining parts for training, right? Then you can imagine for a particular hyperparameter setting, say C equals to 0.5, right? I use these 4 parts for training and test my learned model on part 5. I got 1 accuracy, right? This is not sufficient because I just use 1 part for test. And next, I got accuracy 5, right? And next, I'm gonna use part 4, the second part, the fourth part as a test. Then use the remaining parts for training under the same choice of hyperparameter, say C equals to 0.5, right? And then I can get my another accuracy, right? I keep doing this, right? In the third round, I use part 3 as my test set and use the remaining parts for training, right? Then I can get the generalization accuracy estimate of my choice of C, which is accuracy 3, right? I keep doing this until I used up every part for testing. So I got 5 generalization accuracy estimates, right? Then I take the average of these 5 accuracies as my estimate of the generalization accuracy of using this particular hyperparameter. Okay. This is called k-fold cross-validation. It's very simple. Okay. Then my final performance is accuracy plus accuracy 1 plus 2 plus 3, 4, 5 until 5. Right? So doing this 5-fold validation, you only get the evaluation of one particular hyperparameter choice. For example, C equals 0.5, right? So now I want to pick up the best one. How can we do that? Right? I can set a possible candidates of the state choices, right? I can set it to be 0.01, 0.1, 0.2, 0.5, 0.6, 0.8, 1.0, right? So we assume that, okay, this is the range of the hyperparameters, right? Now, for every choice of hyperparameter, we're going to run this k-fold cross-validation to get the generalization performance estimate, right? Then once we test the performance of every hyperparameter, then we just compare which one is the best, right? And then we choose that one. This is called cross-validation, right? Repeat for every hyperparameter choice. Okay, I think that's it. So finally, I want to summarize this again, right? We want to train a classifier using a given data set. We know how to train given hyperparameters, right? How do we know what is the best hyperparameters, right? We evaluate every hyperparameter using cross-validation, right? Then we pick the best one according to the cross-validation performance. And finally, we use the selected hyperparameter to retrain on the full data. Remember, doing the cross-validation, we actually just use part of the data for training and test on the remaining part of data. But once we have selected the best one, then we're going to apply this best one over the entire training data set, run again, and this is our final model. Okay, any questions so far? Okay, yeah, let's stop here. See you on Thursday.